All right, so it's time for the second part of the fundamental theorem of calculus. It's this is the one that says if you take an accumulation function, as you can see in here, a definite integral from some constant value a, doesn't really matter what that equals. In fact, the value of a is completely irrelevant. But if you go from a up to x, well, it's not completely irrelevant. Sorry, it's sort of relevant. It has to be within the domain of the function or whatever, but it doesn't affect the result. If you go from a up to x, so that you have this like variable upper limit of integration, and you're integrating the function lowercase f, then when you take a derivative of that accumulation function, the rate of change in accumulation is actually equal to the function value itself, f of x. Okay, and it didn't matter what a was equal to. So just as a sort of a rough explanation of what's going on here, and I'm going to do kind of a more thorough proof of this in just a minute. Let's say this is y equals f of x, or sorry, f of t here. And you're going from a up to x, right? And we're sort of accumulating this area as we go. The rate of change in accumulation is all happening right here. Okay, the rate of change in accumulation is happening right there. As x changes, you're getting some change in accumulation. And rate of change in that area basically equals the height of that function right there, which is, f of x. That's the rate of change in the area. So the reason that a doesn't matter is because you could have put a there, or you could have put a here, or you could have put a here. It doesn't really matter where a is, because the rate of change is happening at here, right? This is where things are changing. This is just where you're measuring from, and where you're measuring from is irrelevant. If you alter where a is, if you instead of a, you want to use b, remember that you could write it like this, from b to a, and then plus from a to x, right? And this part, t, this part here is constant. So if you alter the lower limit of integration, you want to go from, this is meant to be a b, sorry, b. You want to go from b up to x. If you change that lower limit of integration, then it's just like taking from a to x, but adding a constant onto it. And so then when you do a derivative of this thing, let's call this our capital F. Okay, when you do capital F prime, the derivative of that constant term is going to be 0, and then you're going to be adding the derivative of this integral from a to x. Right, so altering that doesn't really matter at all. You're still going to get f of x right back again. Okay, so that's part of why that x doesn't, or sorry, the a doesn't matter. So quick little example of how this really works in practice. In practice, this is super straightforward. Let's say you define a function f of x equals the integral from 2 to x of sine of t dt. What's f prime? It's sine of x. Done. That's it. You're just taking the integrand, and you're taking that x and you're sticking it in there. Because essentially what's happening, on some level, what's happening is you're taking a function defined as an integral of something, and then you're doing a derivative. And the derivative sort of cancels out the integral, right? Like if you took a function sine of t, you do an integral of that, and then you do a derivative of that, those two operations are in some ways inverses of each other. And so what you get back is just the original function that you started with, which was the sine function, with the x plugged in as its variable. This is basically the same thing, because whether you call it sine of t or sine of x, the name of that variable doesn't really matter. It's the same function. So this part of the fundamental theorem of calculus really demonstrates the sense in which derivatives and integrals, and we're talking definite integrals here, area under a curve, the sense in which those two things are like inverses of each other, and they will sort of undo each other in this way when you try to do a derivative of a definite integral, or a function defined using a definite integral. So that's just a basic example. In the next video, I'm going to walk through a little bit of a more detailed proof of this, and show you a few other examples of how to use it, and then eventually we're going to get to a proof of the first part based on this second part.